Now that you've had an opportunity to see how the periodic law allows us to predict properties of atomic radius, and really in order to predict which atoms are bigger or smaller based on where their atomic number places them on the periodic table, we're going to continue our discussion with ionization energy and electronegativity. Just like with atomic radius, we want to make sure that we can define each of those two properties. We want to make sure that we can identify the trend going both down the group and across a period. And we want to make sure that we can explain each of those trends. So why are they the way they are? And then we want to look at minimums and maximums. So which one has the highest and lowest, or largest and smallest ionization energy and electronegativity. So if we are looking at the first of those, the ionization energy, the first thing we really need to do is get our mind around what the heck is ionization energy. And you might notice that ionization energy has the word ion right in it, which means that we are talking about charged atoms. An ion is always a charged atom. If we're looking at the ionization energy, we're actually looking about the amount of energy that is required to create an ion. But specifically, it's the cations that we're creating. So the definition of ionization energy is the energy required to remove an electron from a neutral atom. The energy required to remove an electron from a neutral atom is the ionization energy. And when we're thinking in terms of ionization energy and why ionization energy would be either high or low, the easiest thing we can do is really consider the size of the atom. So we're going to consider this magnet as kind of being like our nucleus. And we want our electrons to be attracted to our nucleus. There's a force of attraction between this metallic paperclip and the magnet. In order to remove the paperclip from the force of attraction there, I have to put energy into the system. So I have to put a force on the paperclip to move it away. That's kind of like removing an electron from a nucleus. You have to put some energy in to remove it. There's a force of attraction that has to be overcome. But we could really compare the ionization energy based on the size of the actual atom, or the atomic radius. Think about it like this. If our electrons are really close to our nucleus, there's a really strong force of attraction there. And since there's a strong force of attraction, it's a lot more difficult to remove that electron. So it's harder to remove the electron from a smaller atom because the force of attraction is greater when the nucleus is so close to the electron. Whereas if we think about a big atom, now this force of attraction is pretty weak because they're just so far away. And since the force of attraction is weak, it doesn't take as much energy to remove it. So if we think about ionization energy in terms of its relationship to atomic radius, we would say that there's an inverse relationship. If the atomic radius is big, the ionization energy is small. If the atomic radius is small, then the ionization energy is greater. And that's just because the force of attraction really does change based on the size. So again, small atom, this force of attraction is pretty big, which means it's a high ionization energy. It takes a lot of energy to remove. Big atom, this force of attraction is not as great, so this would be a low ionization energy. High ionization energy, low ionization energy. Now think about how that relates to our periodic table. We know that as you go down, the atomic radius gets bigger, which means the ionization energy would get smaller. As you go across, the atomic radius got smaller, that means the ionization energy would get greater. Both of the reasons why really deal with that inverse relationship between the atomic radius and the force of attraction. So we could say ionization energy decreases down a group because there is less force of attraction, so it is easier to remove the electron. And we could say the exact opposite across a period then. ionization energy increases across a period because there is more force of attraction, so it is harder to remove the electron. So ionization energy decreases down a group because there is less force of attraction, so it's easier to remove the electron. Ionization energy increases across a period because there is more force of attraction, so it's harder to remove the electron. So then, if we look at our periodic table, and we think in terms of minimums and maximums again, the largest atomic radius is now going to be the lowest ionization energy. And the smallest atomic radius is now going to be the highest ionization energy. Which means if we're comparing things like scandium, yttrium, and lanthanum, we could say whatever's closest to francium is now the lowest. Lanthanum is low, scandium would be high. Cobalt, rhodium, and technetium. Technetium would be low, cobalt would be high, and zinc, mercury, bismuth, lowest would be mercury. And again, even though this one's further to the right, this one's definitely got less energy levels, so it's a lot smaller. Zinc would be the highest. And that's how we can just use the periodic table and our understanding of an inverse relationship to then predict the greatest and smallest of any grouping of elements. The other trend that I wanted to talk about today, because it's so closely related to the ionization energy, is our trend in electronegativity. So electronegativity is kind of similar, except now instead of talking about losing electrons, we're talking about sharing electrons. So electronegativity is really how hard the nucleus pulls on shared electrons in a bond. So these atoms have to be bonded together. So if we think in terms of two different atoms that are going to bond together, their energy levels are going to overlap, and the electrons that are being shared are actually going to wind up being here in the middle. So then this nucleus is pulling on these shared electrons, and this nucleus is pulling on these same shared electrons. Each of the nuclei will be pulling at a different amount, assuming that they're not the same elements. How hard they're pulling is the electronegativity. We can again look at size, and we can think about forces of attraction. This nucleus is a lot closer to the electrons it's sharing, so the force of attraction is going to be greater. This nucleus is a lot further from those electrons, so that force of attraction isn't going to be as great. So just like ionization energy, this is inversely related to the atomic radius. The only difference is that now we are kind of limiting ourselves to atoms that will bond. And there is one group on the periodic table that you already know where the atoms do not want to bond. And since they don't want to bond, we can't really force them to in most situations. We'll talk about one we can later. But because they don't naturally like to do that, we don't include them in the trend of electronegativity. Of course, the group that I'm referring to here is our noble gases. The noble gases do not generally bond. So for right now, for this mini unit, we're just not going to consider them in the terms of electronegativity. So we're just going to say electronegativity decreases down a group because it is more difficult to pull on shared electrons that are farther from the nucleus. And then we'll say the exact opposite. It increases across a period because it is more easy, or maybe easier, to pull on shared electrons that are closer to the nucleus. And so now, when we think about our entire periodic table, francium is going to be the lowest electronegativity. And up here, we would think helium, but because helium is a noble gas, it doesn't react at all, we have to go kind of next door. Fluorine is going to be the highest electronegativity. Francium low, fluorine high. Trends still hold, so lanthanum would be low, scandium would be higher, technetium would be lower, cobalt would be higher, mercury would be lower, zinc would be higher. And really, we just need to remember that noble gases don't count at all in terms of electronegativity. Now, you might ask, why not hydrogen? Because hydrogen only has one energy level, so shouldn't it actually be even higher than fluorine? And the answer is actually why hydrogen's here and not over here. Hydrogen doesn't want to gain more electrons. Hydrogen's common charge is a +1, so even though he's small, it is fairly rare for him to gain electrons instead of losing. We call those things hydrides, and they're definitely much more rare than the acids that lose or just have the proton left. One more thing about electronegativity is that sometimes you're going to see atoms that are considered high electronegativity referred to as an electron hog. So when you see that, I don't want it to throw you off. Electron hog just means that they're hogging all the electrons to themselves. That's a high electronegativity. Now before we go, the last thing that I want to do is just make sure that we have all three of these trends, all three of these properties listed on a periodic table together. So just starting with the first one we looked at, as we go down the group, atomic radius increased. Remember, there were more energy levels. Atomic radius decreased across the period because you had that greater force of attraction, which means francium was the largest atomic radius and helium was the smallest atomic radius. Then we had electronegativity and ionization energy. So ionization energy was the opposite of atomic radius. It decreased as you went down since it became easier to remove the electrons. It increased as we went across since it became more difficult since they got smaller, which means that francium was also the lowest ionization energy and helium was the highest. And then finally, the last one we did today, the electronegativity. Electronegativity also decreased as you went down. It also increased as you went across. So we would say electronegativity and ionization energy are directly related, and electronegativity and atomic radius are inversely related. The lowest electronegativity was francium, and the highest would be up here, but because we don't count the noble gases at all, we're going to say the highest is now fluorine. And I'm just going to put on this periodic table, noble gases do not count for electronegativity. And then once we have everything on the periodic table together, we can just use the periodic table to answer all the questions about the minimums and maximums within any list of elements. If you have any questions, absolutely reach out. Otherwise, make sure that you are practicing labeling your table so that when it comes time for quizzes and tests, you're able to make yourself a resource like this so that you can easily answer these questions.